Here's another helpful video I'm trying to create for you guys since you just finished up your test and stuff for homework number 4. Now, homework number 4 is on sections 3.1 and 3.2 that we started actually before you had your test, and then like I said, I finished up both those videos, 3.1 and 3.2, which is on rings and on the idea of subrings. So the difference between what you did in chapter 1 and 2 and now what you're doing in chapter 3 is this: you no longer have integers. That's where most people make mistakes, because you're going to see very similar questions. That's why I'm getting the structure down on all those problems we did in homeworks 1, 2, and 3 in the test, because that structure with integers is going to play as the structure of rings. So instead of an integer, you now have elements of a ring. And you're allowed to use the little element symbol there. B is element of R. So let's talk about this guy right here. So we have a definition. So I give this one, and it should be in your notes now, that in a commutative ring R, where S and T are elements in R, we say that if S is not equal to the 0 element in R, and S divides T, then there exists an element B in R such that you have an equation, T equals S times B. It's the same thing with the world of integers. When S divides T as integers, there exists an integer B such that T equals S times B. But instead of saying the word integer, it's now an element in the ring R. You've got to be particular. These are not integers. So, in this problem, let A and B and C be elements of a commutative ring R with A and B not equal to 0 in R. If A divides B and B divides C, prove that A divides C. This is called the transitive property for a division in a ring. If you look at this problem, this is exactly what homework number 1, problem number 1 was. It's the exact same setup, but we don't have integers. So I'll get you started on this one. So you start off your proof with the givens. You're given that A divides B, and you're given that B divides C. Now remember, this is my scrap sheet of paper, so this is not my proof. This is my want to show thing. This is what we're given, and what do we want to show? WTS. We want to show that A divides C. A divides C. How do I end up showing A divides C? I want to show you that C is equal to A times some element in my ring R. So I want an equation. So let's start with the givens so I can maybe generate this guy here. Well, given A divides B and B divides C, then by definition of divides, here comes, there exist elements, not integers, elements, pick your favorite letters, X and Y in R. The ring R was given. It's a commutative ring, such that you can write yourself an equation. A divides B, B is bigger. B equals AX. And B divides C, C is bigger. C equals B times Y. So I want to show C equals A times some integer, or some element in R, not integers. So I've already got a C equation, so I can start with that. C is equal to B times Y, and then from there I know what B equals AX, so C equals AX times Y by substitution. But again, I want you to use your big words, associativity, commutativity, and things like that. So C is going to be equal to A times XY by associativity. Okay. And then as we continue on, well, I've got my equation. But Y is X times Y, an element of ring R. Well, since X and Y are in R, then X times Y is an element of R, because R is a ring, and ring has closure property. Therefore, as X times Y is an R, a definition of divides, A divides C. So it's exactly what we did before, but I want to emphasize, don't use the word integers. You want to use elements of a ring R. So I'm just trying to get you acclimated to that. So for problem number 2, again, it's very similar, but here where most students will have a problem with is trying to create that equation. So let me tell you. Let A, B, C, F, and G be elements of a commutative ring R with A not equal to the 0 element. Prove that if A divides both B and C, then A divides BF plus CG. Okay. Note that in a commutative ring, S and T are elements in R, and S divides T if there exists an element B such that T equals S times B, and S is not 0. So by definition, it divides again. So what I want to show down here, what I want to show is that B times F plus C times G is equal to, and I'm going to be able to factor out an A. A times some element in R. That's what I want to show. I got to come up with that equation. Basically, that shows that A divides BF plus CG. Again, this is my scrap sheet of paper that I'm working on here. This is what I want to show. A divides BF plus CG, which means I want to show BF plus CG equals A times some element in R. Well, what are you given? You're given that A divides both B and C. What does that mean? Well, by definition divides, write that in, by definition of divides, there exists elements, call them integers, you get like 20 points off. There exist elements x and y such that, let's see here, if A divides B, B is bigger, B equals AX, and if A divides C, C is bigger, C equals A times Y. So I got these little bitty equations. I want to show this guy. Now here's where most people have their problem at. So I'm going to draw my little line down here as we continue on. You want an equation with BF plus CG equals. Well, who's F and who's G? Who cares? They're just given to be arbitrary integers. So here's the trick. What you do is you start out with as BF plus CG. Write yourself an equation. What will this guy be equal to? You can already start with this side of the equation because you're given given B, F, C, and G are all elements in a ring R. Then who is BF plus CG? Well, that would be equal to, I could replace the B with AX times F, plus I can replace the C with AY times G, and that is by substitution. Okay? So I've got an equation. You want equations with this stuff, and all I did was start with what I wanted and then start plugging into it. That makes an equation. And then I believe you got your A that's in common on this guy, so you can factor it out. That factoring is a distributive property, part of the ring. So by the distributive property of being a ring, so it would be BF plus CG would be equal to A times X times F plus Y times G. And then since X, F, Y, and G are all elements of a ring R, then X times F plus Y times G is an element of a ring R. And then by definition divides, you won the game. So again, it's the setup. This is where people typically have a problem. They don't see an equation and I've given them. Well, you got the things you want to substitute, but you got to create your own big equations. So start with one side and then start plugging stuff into it, and that will create an equation. Now, problems number 3 and 4 on this homework set is about showing a subring. So remind yourself from section 3.2, to prove you got to have a subring, show subring, want to show a subring. And you will be quoting the famous theorem 3.6. You should have memorized by now. Theorem 3.6 says this: To show this, you got to show it's 1, it's non-empty. To show it's non-empty, you want to show 0R is an element of whatever set. We're talking about the AX set here, AC set here. The second thing you want to do is show closure under subtraction. That means if A and B are elements of this AC, then A minus B is an element of AC, because as we define subtraction as adding the additive inverse stuff. And the third thing you want to do is you want to show closure under multiplication. That means that if A and B are elements of this set AC, then A times B has got to be an element of AC. Now that's basically the idea of how to show a subring. Look at what I gave you. In this problem, let C and n be a fixed pair of integers with n being greater than 1. Prove that the set, and it's all about being able to read the set notation thing, prove that the set AC is equal to the equivalence class X in Zn. Now, I picked a ring that you already know about. Equivalence class X in Zn such that X times the fixed C equivalence class is equal to the 0 equivalence class. We're going to prove that set is a subring of Zn. So what this really is, you're focusing on C inside of Zn. So all the elements you can multiply by C and get 0 are going to form a subring. The guys you get to multiply by C and get 0 are called the 0 divisors of C. The 0 divisors of C in Zn will actually form a subring. Okay? So, but remember, you have a particular ring structure here, so you don't have to be so arbitrary. We got a bunch of pointy brackets on this stuff. So, you got to show it's non-empty. So, as Zn is a ring, then equivalence class 0 is an element of Zn, which it truly is, but it's a ring. That's the main thing we're focusing on. Okay? And as the 0 equivalence class times a C equivalence class, what's 0 times C? Well, how do you multiply equivalence class? You put one big pointy bracket around it, 0 times C, which is equal to 0. Okay? So a 0 equivalence class times C equivalence class is back to 0 equivalence class. Hence, 0 is an element of AC. You're done. Now, how did I show that? All right. Look at that set notation. This is key right here. You got to be able to read this set notation. This is where you come from. You're an equivalence class in Zn. And you got to show me that you have this property. When I multiply U times C, whatever U are, whatever X, whatever letter you're playing with here, when I multiply it times C, you should get the 0 equivalence class. So let me underline this. 0 is an element of Zn. It's just obvious, part of Zn being a ring. Also, part of equivalence classes, equivalence class 0 times C does equal to equivalence class 0. So where I come from and what property I have been satisfied. Where I come from, what property do I have been satisfied. That puts 0 inside of AC, and AC is non-empty. That's your first part. Okay? We're using the 0 equivalence class in this one. That's one paragraph down, 2 more to go. The next part is you got to show closure under subtraction. You got to give yourself 2 elements. So give myself 2 elements. Let, pick different letters, P and Q. Equivalence class P and equivalence class Q be an element of this AC. You got to pick yourself a couple of elements inside your set. Now that it's non-empty, you know there's some stuff there, give yourself 2 of them. I'm calling them P and Q. Then you describe immediately what that means. Well, according to the definition here, therefore, equivalence class P and equivalence class Q are elements of Zn, and you have the property when I take equivalence class P times C, that'll give me 0, and equivalence class Q times equivalence class C, that will also be equal to 0. These are my properties. I want to talk about closure under subtraction. Well, since equivalence class P and equivalence class Q are elements of Zn, then equivalence class P minus equivalence class Q, which by definition is equal to, how do you subtract equivalence classes? You basically make one big equivalence class. Equivalence class P minus Q is an element of Zn. Why? Because Z mod n is a ring. And rings have closure. This is the big ring here. The rings have closure. Also, so I've got P minus Q equivalence class inside of Zn. Now I've got to show you that I have this interesting 0 property here. Also, when I take equivalence class P minus Q times equivalence class C, that would be equal to, parentheses, equivalence class P minus equivalence class Q times C by substitution. Thus, equivalence class P minus Q times C would be equal to P times C minus equivalence class Q times C by distribution. Hence, equivalence class P minus Q times C is equal to, well, P times C was equal to the 0 equivalence class, Q times C was the 0 equivalence class, and 0 minus 0 is the 0 equivalence class. So, property of 0, if you will. Okay? Additive identity there. You're adding 0 or subtracting 0, you still get the same guy again. Hence, therefore, better words. Therefore, equivalence class P minus Q is an element of AC. Why is it an element of AC? Again, I'm going to go back over here and talk about the structure. AC is equal to all the elements at X that come from Zn, such that when I take X multiplied times equivalence class C, I should be 0. Where do I come from, and what property do I have? Where does P minus C come from? P minus Q is an element of Zn. Also, the other part is P minus Q equivalence class times the 0 equivalence class is equal to 0. Where I come from and what property I have been satisfied, that's what puts equivalence class P minus Q element of AC. Now you've got the third part of this thing. So any one of these trying to prove a subring, you got to do 3 parts. Part 1, show it's non-empty. Part 2, which is the hard part, is show it's closed under subtraction. Part 3, you got to do, use the same guys. So you use as P equivalent class and Q equivalent class are elements of AC. Show closure under multiplication. So I'm going to go back and use the same structure here, but I'm going to replace that subtraction with times. So it'll be times, and basically watch the algebra on this thing, but when you do times, you don't have to distribute, you just got to associate. Q times C will still be 0, and 0 times anybody is 0. So you kind of follow the pattern again. I'll let you guys do that on your proof. And then number 4 is this one. This is very similar to the problem I did on your section 3.2 video on proving subrings. Let R be a ring and let Z be a fixed element of R. Prove that the set, and once again that set notation, Set M, which is equal to x elements of R, such that x equals z times s for some element s and R is a subring of R. All right, so what are you trying to prove is a subring? Well, first thing, R is a ring. That's going to be your overring. R is your ring, and Z is a fixed element. So you're given Z in R. You want to prove that M is a subring of R. M is the elements X from R. Got to show me that you come from R. You've got to show me that you are equal to Z times somebody. We've got third part where that somebody came from R. So there's three things you actually have to show me on this thing. Usually when they have this afterthought of X is equal to Z times somebody, for that somebody in R, that's when I typically use subscripts on these arbitrary letters. You'll see that, okay, and within the proof. Because all of a sudden they threw in an extra letter at me. That's a great thing for start doing, to show the structure on these things. That's a great time for subscripts because you want to keep that same structure. So subscripts help you keep that structure. So if I'm going to prove I have a subring, I'm going to quote my theorem. So that WTS again. This is a scrap sheet of paper. I never get to see this. I want to show a subring. What I really want to show is M is a subring of R. How do I show M subring of R? I'm going to quote my favorite theorem 3.6. So, in terms of your proof, part one, I got to show it's non-empty. Given, start with your givens. R is a ring, and Z is a fixed element in R. Z is an element of R. Okay. Well, since R is a ring, rings have a zero element. The zero element, I'll call it 0 subscript R, is an element of R. Since R is a ring, 0 in R is an element of R. And so I've got that. And as I got to have my structure, 0R, my element, is equal to Z times what element when I multiply by Z is going to give me 0 in R? 0 in R, of course. 0 in R times Z equals 0 in R, where again 0 in R came from R. Hence 0R is an element of M, and M is non-empty. It's usually pretty straightforward to show you 0 has all the properties that you want here. So all things have been satisfied. Three things. 0 in R is an element of R. 0R equals that equation structure Z times 0 in R, where again that 0 in R came from R. So all three parts have actually been checklisted there. So 0R is an element of M, and M is non-empty. Now on this problem, compared to the one that I did in the on the video on section 3.2, Z is fixed, but Z notice location of variables, because rings do not have to actually commute under multiplication. Z is in the front. If you look at the problem that I did in terms of the video, I did a B, but I put him in the back. So location is everything. This time Z has got to be in the front. So the next thing I want to do is show closure under subtraction. So I've got to give myself two elements. So let P and Q be elements of M. What does that mean? That means that P and Q, or thus, better English here, if I get English, thus P and Q are elements where they come from, are such that there exists an S1, great time for subscripts, and an S2 elements of R such that I have equation with the proper format. P is equal to Z times S1, and Q is equal to Z times S2. So I've got my structure to this thing. I want to talk about closure under subtraction. As P and Q are elements of R, then P minus Q is an element of R, but that's statement reason, because a ring. And that's good enough. And it comes from the closure aspect of a ring. Remember, to have a ring, you got 8 properties. It's one of the 8. It's closure under subtraction, which is a part of your ring property, since we've defined subtraction as adding the additive inverse element. Also, I could look at the structure of these guys. Also, who does P minus Q, who's that going to be equal to? That's going to be equal to Z times S1 minus Z times S2, and that's by substitution. Thus, P minus Q is equal to Z times S1 minus S2 by factoring or distributive property. Distributive factoring. So, look at my structure here. I've got P minus Q and R. I got P minus Q equals Z times somebody, but I got to get that third case. Why is that somebody in R? Well, since S1 and S2 are elements of R, that's where they came from. S1 and S2 are elements of R. Then S1 minus S2 is an element of R because R is a ring. Therefore, P minus Q is an element of M. And I have my closure under subtraction. Again, I will highlight what I need here. And then what I need is, I got P and Q. I'm going to look about P minus Q. So I gave myself a couple elements inside of M. That meant they come from R. And there exists as S1 and S2 in R, so I have my equation. P equals Z times S1 and Q equals Z times S2. I'm interested in P minus Q. Well, P minus Q is an element of R. So the first block of being inside of M is taken care of. Also, P minus Q is equal to Z times somebody. There it is right there. P minus Q equals Z times somebody. Z is in the front, very important about location, times somebody, S1 minus S2. And the third thing is that somebody, the S1 minus S2, had to come from R, which it does. So all 3 things have been satisfied. So I've got closed under subtraction. Now for part 3, you're going to do the closed under multiplication part. And then how you figure, so you start as, and you use the exact same elements and the exact same setup. But once you start talking about your equations, you got to talk about the idea of P times Q instead of P minus Q. So you're going to show the closed under multiplication, and once you've got that, then you say, therefore, by theorem, favorite number, 3.6, M is a subring, and don't just stop it there. Your sub of somebody is proper etiquette to describe who your subring are. M is a subring of R, because all the elements came from R. Subring of R. And then you're done. So I'm trying to give you more hints on this particular homework set, but the big deal is don't use the word integers, but there's that structure format that we're looking at, stuff like that. So hopefully this is helpful in terms of getting your homework number 4 done. So you've got to finish up section 3.1 and 3.2 so you can get this homework done, and this homework is due Tuesday, I believe, at 11:30. I gave you some extra time on it.